start with linear regression. So what we are doing, we have a bunch of data and we have two things. One is the response variable. So this is the name I am familiar with most, is the Y variable that you call, that you are trying to predict. We call that the response variable. And then you have the regressors, which are the variable you're trying to use to predict the Y value. So linear regression basically is a linear kind of relationship between these two things. Okay. Now let's step back and try to see what we are doing. We have some variable Y. In linear regression setup, it's usually like a continuous value. Sometimes like minus infinity to infinity, or sometimes some within some range. And then we are trying to predict this continuous value based on some other variables, which can be discrete or continuous. If it's discrete, then you probably already know about that one-shot encoding kind of thing. So that indicator, so if you have a Boolean kind of variable true, false, you convert that to 0 or 1.
Yes.
If you have a variable which can take, say, maybe red, green, and blue, 3 colors, then you have indicator for red and indicator for green, and the blue is automatically calculated from that.
Indicator
Makes
meaning
sense?
a numeric value.
Meaning it will be numeric value, which will be 1 if it's actually red and 0 otherwise.
Yes.
So this is called the one-hot encoding. Like you convert the any kind of classification kind of thing into zeros and ones. So
Yes.
any categorical data is converted to numeric data, which my regression method would be able to handle. Now, this is in general called a regression problem. The regression problem means that I am trying to predict a variable Y based on some other variables. Now, most of supervised machine learning is basically two problems. One is classification, another is regression.
Wait, sorry. So even these words here, Sujay, I
Yeah.
just don't
So now
understand.
let's
What
focus
is
on this word. So there is something called supervised machine learning,
okay?
which usually covers two kind of problems. One is the classification, another is the regression.
And another is regression. Okay.
Now, classification means that I will come back to what supervised means later on, but let's start with the same thing. So in the regression, I had the X and the Y's were numerical variables. In classifications, Y, instead of being numerical variable, is one of the few categories. I want to predict whether this person has cancer or not cancer. Or I want to predict whether a particular person is male or female. Or I want to predict email is spam or not spam. So these are all Boolean classification, where the answer is yes, no kind of thing, or some two values classification. But you can have multi-category classification as well.
So is then that the discrete versus is classification for discrete and then regression is for continuous?
Yes, regression is for continuous, except that the classification is discrete in the Y, not discrete in the X.
Discrete
So
and
both classification and regression allows discrete and continuous in the X values. So the distinction is between whether the Y is continuous or Y is discrete.
yes. Okay.
Okay, that's the first distinction. And the second distinction is sometimes your data actually might be that the Y is discrete, but still you use some kind of continuous methodology. An example would be, say, I'm trying to detect whether someone has cancer or not cancer. And that is based on, say, a certain bunch of variables. And then I can set up a regression kind of model, which will give me a probabilistic setup for this. You probably have already done this, those logit regression kind of stuff.
Yes.
So this is where logit regression falls. There, the response is actually binary. So it looks like a classification problem, but we are setting it up as a regression kind of setup.
Because
where I am so I'm linking the discrete binary variable to the regressors via some logit function. So that's the logic. Logit is basically the linkage between a binary response and the actual regression going on underlying.
Got it.
And then, as you know, we can generalize, like there can be multiple choices of the distribution, like binomial, Poisson, normal, and maybe a few others. So binomial is the relevant one for logit because the response is 0, 1. If it's a counting kind of thing, then the Poisson would be more relevant because Poisson can have values 0, 1, 2, 3, 4, which is like a relevant thing for if it like a count data kind of thing.
Where does the distribution come into play now? I'm sorry, let me make the connection here.
Yes. So this is about the generalized linear regression kind of thing, where we have a response y,
Yeah.
which can take certain values. In
Yes.
case of binary response, it is
The
only 0 or 1
distribution.
or true false.
Okay.
In case of discrete, it can be 0, 1, 2, 3, 4 onwards, but only integers, positive integers or non-negative integers. And in case of continuous, it can be anything between -∞ to infinity.
Yes. Okay.
Okay.
Yep.
And that's kind of restricts our choice of what distribution you want to use.
Got it.
Because if it's binomial or Bernoulli for a single point, then the response has to be 0 or 1.
Yes.
So if you see something where it's naturally there is only two possible values for y, then Bernoulli is a natural choice. Okay. So you choose
Yes.
the distribution that way.
Yes.
And then, so suppose I have chosen Bernoulli, then the Bernoulli has only a single parameter p, which is the probability of success.
Yes.
Now, the question is, how do you link this probability of success p with your regressors? So p has to be a function of x, and that linkage is done by the linkage function. So logit is a choice of linkage function, and
Linkage
if you
function.
choose logit as your choice of linkage, then it's called logistic.
Can you give me some other examples of linkage functions then for
Yeah. So for example, you can, so for logit, the linkage function logic looks like this: log of p over 1 by p, p over 1 minus p is the mu thing,
that makes
which is
sense.
usually linear combination of the xi's for
Okay.
x beta.
I'm sure we'll be deriving all of these and everything too in class, right?
Yeah, you will deriving, but I don't want to get into the maths right
No,
now.
I
It's
know,
not
I know. I'm
important. It's
just
a,
I'm assuming that
definitely.
yeah.
Definitely, we'll do the maths. Yes.
Yeah. We'll do the maths exactly.
In fact, let's do this. Can you open generalized linear regression wiki page
Oh yeah,
that
that's
might
a
have
good idea.
the formulas just to
That's a
have
good
the
idea.
discussion easy?
Generalized
Linear regression.
linear regression.
There should be a wiki page, hopefully by this name. Yeah, GLMC.
I remember we were looking, oh, okay, logistic regression, mixed logic, ordered logic.
Yes. So all those things covered. Now scroll down to the model components or something where we can see. Yeah, you can read this whole page once if you want. It's very useful.
Nice.
It's
Okay.
very well written also.
Bernoulli.
Yeah, scroll down to the overview or sorry, in the model components or yeah, below the overview. Yeah. So yeah, stop here. So you can see that you have the y, which is considered from some probability distribution. And people usually talk about exponential family. Basically, the probability distribution is e power something, something kind of formula. And then you have a linkage uh, such that expectation of y given x is some function of the x beta. And they have introduced a parameter eta in between just to make the linkage.
Got it.
So this is the general idea. And then for each of these, so for the first part, y, you have multiple choices of distributions. For the last part, linkage, you can have multiple choices of the linkage function. And then linear prediction is the most standard one, but you can use non-linear also.
Got it.
Okay.
Super interesting.
Other examples of the linkage function can be something called probit, which is like the normal distribution is used as a linkage, normal
Interesting.
CDF.
Yes, normal CDF.
So just like you want the probability to be between 0 to 1.
There we
So
go.
normal distribution CDF also lies between 0 and 1. So that's like a valid linkage. So you can see there are some link functions thing. For Poisson, the logarithm is the natural linkage function.
Yes,
And for Bernoulli and binomial, the logit is the linkage function naturally.
logic.
So these are the canonical ones. I think you also learned that a little bit in the course. So there is one choice where the final maths comes out to be very easy, and that's what is called the canonical linkage. But
Okay.
there are other choices as well.
This column is helpful. This shows the support for the distribution.
Yes,
So you can see
yes.
when we would use each of
You can
these.
see. So that's basically allows you to choose, depends on your data, what distribution I should choose.
But it all still comes to linear regression though, right?
Yeah. So all of these are like some kind of generalization of the linear regression thing.
Yes. Which one is I guess the Bernoulli you're saying is common.
Bernoulli is very popular. And for normal, it's normal. So normal is like if you choose normal as your distribution and use the canonical, that is like the linear regression you have studied.
Got it. Linear response data. Okay, interesting. Okay, yeah, Sujay.
And then the last two, multinomial, etc., is also like very standard used.
Okay. What is an example of a multinomial here?
So multinomial is like something you're classifying and it can be one of say 10 different things and you're trying to predict which one it is.
Got it. Sorry, I'm just gonna ask random questions, but
Yeah,
does
yeah, sure.
I've heard of this thing called clustering. Doesn't that kind of
Yes.
do the
Yeah,
same?
clustering is kind of related but different. Clustering is you're trying to predict individual points which falls into which one. Here, the final output will be like, okay, so your probability of success, your probability of having cancer is 80%. In clustering, you will classify, okay, this is a cancer patient or not cancer patient.
Got it. Okay. Oh, everything is coming in. Markov chain, Monte Carlo,
Yes,
least squares, Gauss Markov.
yes. So this is a very general framework which covers a lot of things that we do.
Super cool. I hope they give good examples in class, Sujay, because that way.
Yes.
Ah, here we go. Okay, some cluster data. Okay, generalized looks. Sorry, I'm blanking again
Yeah.
here too. What is the difference between generalized linear models and generalized linear mixed models?
What is a mixed model? I don't remember this one. This is further extension on that where
Random effects in
random
the,
effects in the linear predictor. I don't know much about this one.
okay, interesting.
At least I don't recall the name.
GLMMs. Okay, maybe we'll see that. Okay,
Yes,
this is
and then there is something called generalized additive model where you have multiple functions and all that.
oh geez. Okay. Yeah, is there ever a way to like combine two of these I don't think that's really applicable, right? You would never like use Bernoulli and Poisson at the same time or something, right?
You probably don't need to, but yeah, I can't. But you can have like multiple response kind of thing. So you're
Ye-
trying to predict two things simultaneously,
Oh,
one of which is yes, no, and another is a count.
got it. Yes.
And it may be possible that the count will be positive only if it's yes.
But then you'd use,
Otherwise, the count has to be zero. So your joint prediction has to be consistent that way.
I'm gonna do a review of all the distributions also. I think that might be a
Yes,
help.
yes, that might be super useful.
Yeah, at least like remember all the ways that when to use which distributions and things like that too.
Yes, yeah, yeah, that and also if you go to the wiki page for distributions, it will tell you the connections between the distribution. That is also very useful. Like
Yes.
how does chi-square relate to normal and that kind
Yes.
of things.
Yes, I think that'll be good too. Okay, let me write some of this down here. This one was called Wikipedia Generalized Linear Models. Wikipedia Generalized Linear Models. And then distributions. Um, They are related. Okay, this is a good one to know. So where were we? We were on the supervised, so we covered classification, and then we were talking about the regression, right?
We kind of covered regression. Classification, there is a different kind of like altogether thinking that I am to, but like my final answer is it belongs to this class or that kind of thing.
Yes.
So people's approach is different, and then there are some standard ways of classification like k-means and sorry, nearest neighbor kind of classification and that kind of thing.
Next neighbor.
Now, yeah. So nearest neighbor is basically you have a data point to find some 100 nearest value closest to that and take the average of those or take what is the maximum or majority of those are saying.
Can you give an
So
example?
suppose you have, yeah, so suppose you have a new patient whose some bunch of 15 different parameters are given to you and you want to tell whether this person has cancer or not.
Okay.
So now you maybe have your hospital has a database of say tens of thousands of patients already, and you find some 10 or 15 patients who are closest in terms of those parameters to this new patient. And out of those 15 data points which are closest to this patient, maybe 12 are saying that no cancer, 3 are saying cancer. Then probably this person has very likely not cancer.
Got it. Interesting.
So this is how you can do things. And as you can see, realize this doesn't require any technical knowledge or anything. And this is
Yeah,
very easy to do.
it's just
This is
kind of
almost like anyone can do it. You don't need a doctor to do it.
putting it into
That
buckets.
kind of, yeah, we are doing a trick like that. Yes.
Yeah.
So now this may not work always very well, particularly when the thing you're trying to predict is rare.
Ah,
Because then like if 99% of the population always don't have it, then any kind of 15 or 100 or whatever majority will say it's not there.
yes.
So you kind of have to do some kind of boosting of the population percentage
Well,
or
that's
something kind of thing.
another word
Yes.
somebody asked me
Yes.
in the holiday party. What is boosting, Sujay?
Yes. Yes. So boosting is basically techniques of like making your data set biased in certain ways, and there are maybe multiple ways of doing it to improve your prediction rather than what the data will ordinarily tell you.
So like a weightage?
Yeah, I can think of it like a weightage, but people try to do it in a slightly smarter way, and there are multiple ways to do that.
That's the gradient boosting, right?
Yeah, I think gradient boosting is that.
Okay. Okay, so classification, you said k-means clustering would be there.
Yeah, that is like not k-means, k nearest neighbor.
K
Now, clustering is a different problem, and clustering doesn't really